Hi, everybody, and welcome. It's Professor Thayer, and today we are going to talk about solving the second-order linear homogeneous differential equations. So, first of all, you may be wondering, why do we need to solve this thing? And do we really need to know how to do this? So let's talk about that. So, actually doing a bit of an experiment today. I'm going to be talking to you on screen, but then we're going to move over to doing some recording off of my tablet, which I haven't done in a while. So hopefully this all works. And last time I started doing this, it made some grating noises for some reason. But anyways, everything seems normal now. All right, so in quantum mechanics, there is an equation called the Schrödinger equation. You might have heard of it, H psi equals E psi. We will have a whole day dedicated to working with the Schrödinger equation. What's it all about? Well, the whole thing about this is that we're trying to understand where electrons go, and this is really important for understanding how atoms are made, right? And how they join together to make molecules. So what we need to know is, well, like, why do we have the octet rule, and why do we have the bonds in the places that we do? Why is there the tetrahedral carbon? I mean, you know about this from Gen Chem, about moving things to space them around, but why are there the orbitals that we have? And that's what quantum mechanics will help us to understand. Now, when we do quantum mechanics, we're not actually answering the question where the electron actually is. We know from the Heisenberg uncertainty principle that we met last week that actually you cannot actually know with 100% certainty where the electrons are anyways. So what we can know, however, is the probability of where they are, where they're most likely to be, which is going to be somewhere near the nucleus, but in fact, they could be anywhere in the universe. So in quantum mechanics, the Schrödinger equation will tell us the evolution of the wave function when we're doing the wave application, which is what we'll do next. That'll be psi of x and t, which encodes the probability amplitude to find a particle at a given position and time. And that one, we actually do get out the actual position and time. So the solutions are not the locations, but rather the square of the function's magnitude. So we have this idea of the psi squared, or psi star psi, to be more precise, which gives the probability density for the particle location. Might sound a little bit strange, but once you know what the psi is, you can find out all the other information that you want to know. So when we move into the quantum mechanical world, which also uses a very similar waveform, you need to solve for where the particle is. You cannot solve for it directly because we don't actually know, and we can't not measure it because of the Heisenberg uncertainty principle. But we can say about the probability of finding it. So that is why we will be solving for the psi squared, and then we will use that to find out the information that we want to know. But what exactly is psi? It is the second-order linear homogeneous differential equation is what we will use to actually find what the psi is, which will tell us about where the probability of the electron is located. So what we want to discuss first is how to actually recognize a second-order linear homogeneous differential equation. Would you know one if it came out in BitU? You may not. And so I think it is time for us now to switch over to the OneNote board. So I'm going to turn off my camera because I'm going to flip this laptop over, and you'll be looking at the ceiling, which is not very exciting. Next, I'm going to share my screen. Hopefully it shares the whole thing. Just sharing screen, okay? And next, I'm going to put up the whiteboard. Let's put this full screen, and this is my controls for the Zoom meeting. All right, so hopefully you can still hear me and see the laptop. This is making some weird noises. Oh, that seems alright. It's like some feedback or something. Okay, so let's give this a try. And the pen is not writing. Interesting. Let me pause this for a moment while I troubleshoot the pen. No, not what I would like to pause is the recording. Hmm. All right, that seems to be working. Let me try share screen again. Share. Okay, so now it says I'm screen sharing, and let's go full. All right, so I don't know what was going on. The pen seemed to freeze for a minute there. All right, so second order linear homogeneous differential equation. So what we want to do is how to recognize. I realize I didn't time myself. How to recognize a second order linear homogeneous DiffEq. All right. So the first thing we need to recognize is the second order part. How would you recognize if an equation is second order? Well, the way we recognize it is we look for the highest derivative. And if it's second, if it's a second order derivative, then it's second order. So you have the first derivative and the second derivative, like a single prime and a double prime. We're looking for the ones with the double prime, or a d squared x or whatever, dt or dt squared, whatever variable it is you're working in. You're looking for the second order. Linear. How do you know it's going to be linear? So this is about the dependent variable. Now, in our case, we have a full function. So I'm going to put variable in quotes like this, the dependent variable y of x and its derivatives. And its derivatives are in linear form, like the line. That's what we have in mind here. Okay, so this means no powers, no sine. Okay, none of these. No powers, cosine, sine, blah, blah, blah. Any funky stuff. You can just have very plain equations. All right, the next thing we want is the homogeneity. What makes this thing homogeneous? So you can tell if something is homogeneous. This is an easy one. It is set equal to 0. And how do you know if it's a differential equation? So you recognize this because it has some derivatives. This is the math equation that relates a function y of x to its derivatives. And this will tell how it changes with respect to an independent variable. In this case, the independent variable is x that I've shown you right here. Okay. So what we want to do then is we want to write down the goal. So our goal is solve for y. It's like a guessing game. I'm thinking of a function. that has thus and such properties. So now what we're going to do is how to solve this thing. How to solve the second order linear homogeneous DiffEq. So it goes something like this. I'm thinking of a function y of x, y, whose second derivative plus a constant p, that constant is called p, times the first derivative plus times the function itself, plus a constant p times the first derivative plus a constant q times the function itself equals 0. This is what we're doing. And it's like, what function am I? This is what we are trying to solve. So we should have a look at what one looks like. D squared y over dx squared plus p dy dx plus qy equals, this is the general form. Okay, let's just pause for a sec and see if we can identify the various pieces here. Okay. Is it a differential equation? That one's easy. Yes, it's a differential equation because I can see that, right, I have some derivatives here. Here's another one, dy dx, d squared y dx squared. Is it second order? This power right here tells us this is second order because it's the highest order derivative is second power. So that's the second order derivative. Is it linear? Well, we'll find out when we get the answer. But there's nothing crazy here yet, right? So the answer y is the linear part. Is it homogeneous? It is right here. Our equation is set equal to 0, and that is how we tell that this thing is homogeneous. All right, great. So what I'm going to do with you now is just go through this in a very general way of how to do this. And this is actually outlined for you on a handout that I have passed out in class and is posted on our Moodle page. But even if you don't have that sheet in front of you for whatever reason, we'll be recording the steps here. So the first step is, step 1 is deduce P and Q by inspection. So what that means is that we need to figure out in an actual given equation what the values of P and Q are. So the way you do this is you just line them up, but you may need to do a couple of things. You may need to rearrange the equations. So you want to rearrange the equation in rank order. And what I mean by that is you put your highest power derivative first, and then your next power second, and so on. And the other thing you want to do is you want to divide through by the leading coefficient. If it is not already 1. So in other words, the coefficient right here should be a 1. So this doesn't have anything there, so it's understood that that is multiplied by 1, so that's all set. But if there were a number here, like maybe if it was 3 or whatever, you would simply just divide out by it to make sure that everything is 1. It may also be useful for us to just do a short little aside here. We have the Leibniz notation. This is the ddx kind of notation, and this was used for the derivative. Maybe you're aware, but calculus was actually invented twice. It was invented by Leibniz, and it was also invented by Isaac Newton. And Isaac Newton had this kind, had the y prime, y double prime. This is like d dx, d squared x, or d squared y dx squared. And notice that the powers get written not in the same place in the top and the bottom in Leibniz notation. These are two different kinds of notation that actually mean the same thing, and you may be familiar with that from having taken calculus class. But anyways, we're actually going to interchange between them when it is convenient for us to do so. So the Newton notation is a lot more compact, but it doesn't explicitly say which variable is varying with what other variable, which is why it's not as useful. So we have in the Leibniz notation d squared y over dx squared plus p dy dx plus qy equals 0. Okay, and so this is the Leibniz, which is the form you'll often see things in. But we could rewrite this in the Newton notation. So you could write y double prime plus py prime plus qy equals 0. This is the same thing using the Newton notation from the calculus. And so that may be a little more helpful for us. So step 2, then substitute into the auxiliary equation. Opportunity to solve. Now, if you know how to solve the quadratic equation, then you can solve this. Now, remember when you learned how to solve the quadratic equation in high school, you realized that there's two roots, right? Because you had the x squared term, so there's going to be two different parts of this. So the answer, it's going to be like this: m squared plus pm. So remember, we just solved for p and q. So these are those m and q's equals 0. This is the auxiliary equation. It's very similar to ax squared plus bx plus c equals 0, which is from your algebra. And remember that we set a equals 1 all the time for our auxiliary equation, which is why it's the way that it is. So how do you solve this thing? Well, you may remember the equivalent one from algebra. X equals negative b plus or minus the square root of b squared, take away 4ac, all over 2a. This is from algebra. But our matching one is going to be m. So we're looking for a variable called m equals, and then look to see how it matches up, right? So instead of negative b, it's going to be negative p. Negative p plus or minus the square root b squared minus 4. Now remember that a is set to 1 in our situation, so we should never have a leading coefficient other than 1. So we can skip that, and then it will be 4ac, which in our case is now q, over 2 times a. But remember, a is 1, so it's going to be over 2. This matches the auxiliary equation. And that's how the solution goes. All right, next thing we do is you're going to need to figure out Step 3, figure out what kind of roots you have. Now, this may sound a little strange, but do you remember that when you solved the quadratic equation, it was really telling us where the parabola crossed the horizontal line, right? It's the x's, it's the y's that tell you that correspond to the x's where it crosses, right? So we're thinking about something like this, right? So you had this and you would have a parabola, right? And you got some points crossing. Great. But what happens if your parabola didn't cross? There are 4 parabolas that do not cross, right? So the answers would be imaginary. So what we need to do is we need to find out what kind of roots we have. They could be 2 real roots, could be 2 roots that are identical. There's another case. So the other solution to this could be a parabola that touches in one spot. So it could be like this double root, right? It could also be this one and any quadrant really doesn't really matter. But you have a double root, right? Is another possibility for the solution of a parabola. And so what we need to do then is we need to figure out what kind of roots we have. So then you use the appropriate solution form. So some smart math people have already figured out what the equation should look like, and all you need to do is just substitute in your values into that equation for the solution for this. So that's what we will do. You have 3 cases. Case 1 is 2 distinct real roots. 2, yeah, 2 distinct real roots. 2 distinct real roots. And if you have 2 distinct real roots, then what you're going to have is the equation y of x equals c1e to the m1x plus c2e to the m2x. And you'll substitute in your values. Case 2 is 2 equal real roots. And so that would be the case where it's sitting tangent right on the line, on the horizontal. And so in this case, you'll have m1 equals m2 equals m, right? So there's only one m. So you will have y of x equals c1e to the mx plus c2e to the mx. So in other words, the answer is almost exactly the same. It's just that in this case, the m's are gonna be different, right? The m1 and m2 are distinct. In this case, the m's are not different, and they are sitting right here having the exact same values. So let's just, for a moment, take note of these. These are your integration constants. These would be solved using the boundary conditions if they're available. But this is why you have the C1 and the C2. They could still be distinct for the situation even when M is the same, and that's why we have 2 terms. Case 3 is that you would have complex solutions. That means the imaginaries. So deduce the A and the B from the answer. So when you have this, you'll have M1 equals A plus BI, where I is the imaginary, and M2 equals A minus BI. Remember, you have this where I is defined to be the square root of -1. The triple equal sign means the definition. So this is something that got defined. Somebody said, well, what's the square root of -1? And there, we don't know. So we made up imaginary. So we have these two solutions to this, A plus BI and A minus BI. And so what we need is the A and B values. They're right here. So you get your complex answer. And then you will substitute into this equation here. So you'll have y of x equals e to the ax c1 cosine bx plus c2 sine bx. Just like so, we'll substitute your a and b's in here. So let's just mark where they are. So you have a right here. A is also here. A shows up here. And the B is the other one. So let's pick a different color for B. Okay, so here's B right here. It's also B here, and B is here, and B is here. And that is what you need to look for and substitute in. And that is how you will solve this. All right, so then we've now seen how to do this in a very generalized way, but you might be interested in, well, what does a real problem actually look like? So I thought what we would do next is go ahead and actually solve a real problem. So here we got, now I will also note that in the scans that I've provided for you, Anton multivariable calculus, this is page 983 to 987. This is an example. This is actually example 2-1. So you can read through that if you want to just see a different way of doing this. We will go ahead and solve that together right here, right now, so that we can see how to do this thing. So let's see what this would actually look like. D squared y over dx squared minus 3 dy dx plus 2y equals 0. So again, we're saying, okay, I am thinking of a function y that has its second derivative minus 3 times the first derivative plus 2 times that y itself equals 0. What function am I? And that is what we are going to try to figure out. Okay, so I really encourage you to do all the steps one at a time, even if you feel like you don't need to write them out, because it's going to get harder as we move along to do more and difficult things. So please just get used to writing out the steps, especially while it's easy. Okay, so step 1 is deduce P and Q by inspection. Okay, so let's actually just write this out. So here is our equation. I'm going to just write it out. 1 d squared y over dx squared minus 3 dy dx plus 2y equals 0. And then I can, this is the Leibniz. And now what I'm going to do is I'm going to switch it over to the Newton form. 1y double prime minus 3y prime plus 2y equals 0. This is Newton notation. And now we're going to write out the form. So I'm going to do it like this. The general form is 1y double prime plus py prime plus qy equals 0. This is the general. And you'll also notice that I'm doing this in a pseudo proof-like form, which also in your answers I would expect you to do, because it really trains you to think about what it is you're actually doing. So P equals -3 by inspection and Q equals 2, right? So you just match them up and see like what's what here. So this is by inspection. And if you switch over to the Newton form and write out your form underneath it, then it's very easy to tell. All right, we're ready to move on to step 2. So in step 2, we need to substitute into the auxiliary equation. All right, and don't forget, we'll be expecting 2 answers. So we're gonna do it like this: m squared plus pm plus q equals 0. This is given auxiliary equation. Then the next thing that we do is we substitute in the values that we just got. So we need the P and Q. They're right here just above. So now what I'm going to do is I'm going to do m squared plus. Now, what I do is I put a parentheses to show that I have substituted something in. That's just the way that I learned to do math. P and Q, which is a good habit. And then I can look at it and I can very visually and easily see what lines up with what. Okay, so there it is. It's substituted in. Now we have this matches to the general quadratic equation. And now we're going to use the quadratic formula. To solve, right? So we have the general form, going to be plus or minus p squared minus 4ac all over 2a. But we had our specific form. So we're going to use this. M equals -p plus or minus square root of p squared minus 4 times 1 times q, right? All over 2 over 2. This is the given quad formula for the auxiliary equation, which follows directly from what we did in algebra. Okay, now what we need to do is substitute in P and Q. So we're going to do it. M equals negative, what was P? P is -3, negative of -3 plus or minus square root of -3 squared minus 4. We can drop the 1, and Q was 2. Double check. Yes, 4 times 2. I substitute that in. All over 2a, which is just going to be 2. And now, so this is sub in E and Q. All right, next what we're going to do is go ahead and simplify this. So m equals -3 is 3 plus or minus square root of -3 squared is 9 minus 4 times 2 is 8 all over 2 equals 3 plus or minus 9 minus 8 is 1 square root of 1 over 2 equals 3 plus or minus, what's the square root of 1? It's 1 over 2. And that gives us 2 answers. We have the positive root. Remember, we have the plus and the minus root solutions, which is what's being given here. So I'll just put a plus and minus over the arrows to remind myself of that. So we have 4 over 2 equals 2. And we have the minus root. So 3 minus 1 is 2. That's 2 over 2 equals 1. So our 2 solutions then are going to be 2 and 1. All right, let me just double check and make sure. Yes, I agree. And what I forgot to write is simplify, which is, oops, stop, close. This is all simplify. which is what all this line is down here. All right. So the next thing we want to do is just make a note. Okay, actually we can do this in step 3, which is select the correct solution form. All right, I'm just gonna note right here, we have 2 real roots. Okay, that's what we got for our answer. And so now this is a case 1. We have case 1, 2 real roots. So we then select the form, which we were given above. So y of x equals c1e to the m1x plus c2e to the m2x. This is the given solution, right? And now we're going to have to sub in m1 and m2. So here we go, y of x equals c1e to the m1. So I'm going to, it actually doesn't really matter which one goes where, but I'm going to do the smaller one first. X plus c2e to the 2x. Okay, that's not a division sign, that's parentheses. Okay. And now we could clean this up. Y of x equals c1e to the x plus c2e to the 2x. That's just simplifying all of that. And that then is our solution. Great. So we should probably put a box around this to show how important this is. All right. Ta-da! We got a solution. Yay. The next thing that we might want to do then is verify the solution. Now let us suppose we want to verify the solution. How would we do that? All right. It was very similar to the procedure that you would do when you get an answer in algebra class. So when you got some x value and you thought you solved it, what would you do? Well, you substitute it back in and demonstrate that the equation holds. And that is what we can do here. But we have all these differential equations, and we're going to need a couple of derivatives. So the first thing that we need to do is we need to get the derivatives. Get the required derivatives. So we do this by going back to the original equation and then getting the required ones. So here we go. D squared y over dx squared minus 3 dy dx plus 2y equals 0. This is the given DiffEq. Okay. Now, we're going to get the required derivatives. Here is our equation. Y of x equals c1 e to the x plus c2 e to the 2x. This is the solution from above. Now, the next thing we're going to need is, okay, now remember that we had the Newton notation and we had the Leibniz notation. So I'm just rewriting this underneath as the Newton form because it simplifies the notation considerably. Okay, so the next thing that I need is I need the y prime, which is the dy dx. So I'm going to say y prime of x equals, well, how do I get that? Well, I just take the solution and I take the derivative of it. So what we need to recall that y prime of e to the ax, y prime equals d dx of e to the ax, which is equal to, how do you do this? What you do is you take this number here and you bring it down, right? So it's a e to the ax. Okay, so this will be very useful because what we're going to do is take exactly that derivative. So if we are taking a look here, what is the derivative of c1e to the, that of course is 1x. So we could go ahead and just write a 1 in here just to remind ourselves. And let me just make sure this x is nice and clean as an x. Okay, so now what we're going to do is we're going to bring down the 1. So I'm going to put that in the parentheses, e to the 1x plus, and then we do the same for here. So we'll bring down a 2, c2e to the 2x. And that is how we solve this thing. This is take y prime. And now the next thing we do is, well, this is kind of a mess. We could really simplify this. Y prime of x is equal to c1e to the x plus 2c2e to the 2x. Just simplify that thing. All right, now the next thing we're going to do is we need to take the y double prime. So y double prime of x equals y prime of x. In other words, take the derivative of the line above. So we will recall the same information. Okay, so we're going to have again 1 c1e to the x plus, and now we have another, so we have 2, so you have a 2 times 2c2e to the 2x. So this 2 in parentheses is the one from taking the derivative. y prime of x. Okay. And now we can clean this up. So y double prime of x equals c1e to the x plus 2 times 2 is 4, c2e to the 2x. And that's simplify. Great. So now what we want to do is, all right, let's zoom out for a second. So remember in the regular algebra, when you get a solution, the way you check it is you substitute it back into the original thing that was given. So the original thing that was given, we've copied right here. Get the pointer out. This right here is the original. And now we have taken the requisite derivatives. They are right down along the side here. And what we want to do is we want to go ahead and plug all these things and ask the question, does it equal to 0? That is how we demonstrate that the solution is verified. So let's get to it. I'm going to zoom back into my workspace over here, and we're going to go ahead and fill that out. So now substitute the derivatives back to the original. All right, so we gotta hold this up. All right, d squared y over dx squared minus 3 dy dx. And notice that I am being very particular about writing out all the steps and writing down what I'm doing. Probably a little bit overkill for this, but it is going to get harder. And knowing exactly what the steps are when you can see it very plainly is very helpful. Because if you learn it now, it will make it easier. This is the Newton form. And now what we're going to do is we're going to substitute in the things. Y double prime. Okay, well, what's that? So we need some new colors here. All right, how about yellow? Ooh, no, we don't need that though. Y double prime. Where's y double prime? Well, go look up here. It's this whole thing, right? This whole equation here is the y double prime. Where is the 3y prime? Well, that's going to be the next one. So let's pick another color. How about green? Okay, this one. Y prime is the one that we solved right here, right? That's this thing. Okay, and where's the y? Well, we already solved for that some time ago. This y here is the y that we solved for before, which we rewrote right here. So now what we need to do is we need to put these things. Oops, sorry. That's organized. Anyways, something like that. You get the idea. They're color coded now. All right, so now what we need to do is we need to substitute this stuff in. Oh, and I should just do, oh, I see what I did. I put the marker on the wrong one, but it's all the same. Y is there. Here, I'll do, this one is this, and this yellow one is this here. Okay, so now what we got to do is we got to fill in the blanks. Okay, so we got to fill out the entire y double prime. It's a big old equation. Okay, so here we go. So C1 e to the x plus 4C2e to the 2x minus 3 times C1 e to the x. I'm just copying from above, which you can't see on the screen right now, but I have it in my notebook. E to the 2x plus actually, yeah, that's probably better. You can see that I'm really just copying from above. Plus 2 times C1 e to the x plus C2 e to the 2x. Okay, so that should be exactly just copied from above equals 0. And this is a sub in. Don't have a whole lot of space here. Okay, each of these I've just substituted in, and the numbers, these coefficients here, came from the coefficients that are out in front of those equations. Okay, so there's the equations. Now what we got to do is we need to group the we need to distribute is what we need to do next. All right, so let's get to this. E to the x plus 4C2 e to the 2x. It's nothing to do there. But this, we do have something. So I'm going to distribute the -3. So I'm going to put a plus sign. So it's going to be minus 3C1e to the x plus -3 times 2 is -6C2e to the 2x. That is this term here. And now plus, and this is this one here, 2C1e to the x plus 2C2e to the 2x equals 0. This is distribute. Now, the next thing we can do is we can group the like terms. So, yeah, we're going a little wild here with the parentheses. There's a little too much here. Let's just make that nice and clean. All right, that's good. Now we're going to need to group the like terms. So it could be helpful for us to just go ahead and find the like terms. I need another color. So we'll take pink. All right, and every time I click, it brings it up. Okay, so my C1 terms, C1 e to the x terms should go together. And now I need another color for the other terms. So the C2 terms should all be grouped together. So let's get to it. I'm going to use square parentheses to make it different from what I did before. C1 e to the x. Oops, that's not an x. To the x. Minus 3C1 e to the x plus 2C1 e to the x. So these, you can see all these terms can be removed from the parentheses. So I'm skipping the step of removing the parentheses, but it's identical as this line that I wrote above here. And now what we're going to do is now we're going to group the C2s for C2e to the 2x. And I'm just using the parentheses for grouping minus 6C2e to the 2x plus 2C2e to the 2x equals 0. And what we really should be doing is putting a little question mark above these because we don't know that they're equal yet. That's actually what we are, in fact, testing right now. And this should be a square parentheses. Match that one. Okay, good. Now, let's find out. Is it equal? So C1 e to the x minus 3 plus 2. So we have all the same terms. Plus 1, minus 3, and plus 2. That adds up to 0. Plus, let's check. 4 and 2 is 6, minus 6 is 6. Indeed, this one also adds up to 0. Equals 0. Hallelujah. Yes, it worked. And so this is now verified. So you can write QED. Quod eram demonstrado. This means what was meant to be demonstrated. You might know it from proofs. It's like when you have done the proof, which we did. All right, so let's just zoom back out for a second and see what we have done so far. So just coming back up to the top, we talked about how to identify the correct equation type. Second order linear homogeneous differential equations. And then we talked about the general steps to solve this thing. And then we actually solved one. So here is our example. Here is our example of actually solving one. So what we did here is we actually went ahead and solved for the P and Q, just these. And then we subs into the auxiliary equation, which is this right here, to get two answers. We got out as 1 and 2. And those 1 and 2 then become the answers that we subbed into the solution form. This is our solution form right here. And what we wanted to do then is verify if this solution is in fact actually correct. So in order to do that, we went back to the given differential equation. And then what we did with this is we also took our x from our equation y of x from above. So these are the two parts, and we want to know, is this in fact actually a solution of this differential equation here? So it's like when you have an x and you're like, okay, is this really a solution of that equation? So then what we did is we needed the requisite derivatives. Well, how did I know which derivatives I needed? I just looked in the equation. It's the first and the second derivative, and they're multiplied by constants. The leading coefficient is 1. Which it always should be. If it's not, you need to make it be 1, but we've made it be 1. It already was 1, so that's good. These are the equations that we had. And so then what we did is we substituted these derivatives back into the original. And when we did that, we solved this thing and noticed that we got the answer was 0, which allowed us to have confidence that the solution that we posited, that is this y equation right here, is in fact a solution of the given differential equation that we had here. All right. Next thing we want to do is we want to demonstrate solving for the values of C1 and C2. This is applying the boundary conditions. All right, so let's move back out to some reasonable next. These are the boundary conditions. This is done. This can only be done when some boundary conditions are no. Right, so let's see what this would be like. So you have to have more info given, in other words. So here we're going to say, all right, let's suppose we look back at the problem. We say, oh, I missed some of the part of the question here. You'd have to have this information given. Okay, let the boundary conditions for the above equation be given as y of 0 equals 0 and dy dx at x equals 0 be 1. All right, so you'll see something like this given to you when a boundary condition is available. The general solution is solved above. All right, so what we should do is start with the general solution. Y of x equals C1 e to the x plus C2 e to the 2x. The way we recognize that this is the general form, again, is because we have these C1 and C2. So our next task is to go ahead and solve for them. So we want to solve for these. That's the objective of this part, solving for the C1 and C2. Consider condition 1. What does condition 1 say? Well, condition 1 says y of 0 equals 0. This is a given boundary condition. In other words, we could write this another way. It's a point. You have the point 0, 0. This is the x, and this is the y. You see that? So that's what this means. X is 0 and y is 0. Now, take the solution from above. Y of x equals C1 e to the x plus C2 e to the 2x. This is above. Now we're going to substitute in. So y of 0, all right, so everywhere you see x, you should write 0 equals C1 e to the x, right? A y for that. Every time you see x, write 0. C2e, we'll put it in parentheses. C2e, the 2 times 0. And then it says equals 0. So we know, so this is like f of x equals a number. So it's y equals equals this. But we know that the y value is 0. So we set this thing equal to 0. Okay, so what we do is we sub in 0, 0 from the boundaries. Okay, now what we're going to do is we're going to simplify. Okay, so y of 0 equals, what's anything to the 0 power? Doesn't matter if it's e is just a natural number, doesn't matter. Anything to the 0 power is 1. C1 times 1 plus C2, oh, here's another one. 2 times 0 is 0, and e to the 0 is 1. It's the answer, equals 0. Great, so this is simplify. E to the 0 equals 1, recall this math fact. Okay, now we can simplify this. Y of 0 equals C1 plus C2 equals 0. And in fact, actually, we could just leave this off because it would read a little more cleanly. We don't even need that. This is the part we need. C1 plus C2 equals 0. This is our first solution. Yay. Okay, but we still don't know what C1 and C2 are. And that's because we haven't applied the second boundary condition. So consider condition 2. What does it say? d dx 4x equals 0 equals -1. This is a given boundary condition. All right. Well, that means we're going to need to use our equation for the y prime, which we had already solved. Now let me just look back up here and see. We had it right here. It's this green one right up here, which I also have conveniently written on my notebook. But let's just take a look at this. And what I'm going to do is I'm going to copy that down to here. I need to use that again. All right. So what this says, and I'm going to use the Newton notation. Actually, I could even write this one in the Newton notation. Y prime of 0 equals -1. This is Newton notation of this one right here. Right? I just wrote it in Newton. Now I'm going to do y prime of x equals. Now I'm actually copying from above. Y prime of x equals c1 e to the x plus 2 c2 e to the 2x. This is from above. Copied. All right. Now we're going to substitute in y prime of 0 equals. Well, every time I see a 0, no, every time I see an x, I put a 0. So there's e to the x for the 0 plus 2 c2 e to the 2x. So I'm going to write 2 times the 0. Okay, and this is sub in the boundary condition. And this equals -1. Why? Because it says y prime of 0 equals 1. Here's y prime of 0 is 0 substituted in where all the x's are. And here's -1. That's the answer. How did I know it? Well, it's the boundary condition. Boundary condition. This is boundary condition 2 applied. There it is. Okay, now we have some simplification in order here. Equals C1, anything to the 0 power is 1 plus 2 C2 E times 2 times 0 is 0. E to the anything to the 0 power is 1. Oops, don't even need the E there. All we need is just a 1. All this whole thing just turns into 1 equals -1. Now, C1, we can even make this cleaner. C1 plus 2 C2 equals -1. Voila. We have another answer. Our second result. We have 2 equations and 2 unknowns. So what do we do? 2 equations, 2 unknowns. Solve the system equation. Now, there are lots of different ways you can solve systems of equations. If you happen to have taken linear algebra, you may know the linear algebra way to do this. There are lots of ways you can do this. This one is actually fairly simple to solve, so I'm actually going to just do it an algebra way. An algebra way, if my pen will come back. Oh, my pen is frozen again for some reason. The last time this happened, it just came back in a minute, so I'm hoping that it will. Hello, pen. Not finished yet. Battery should be good. Hello. All right, let me just pause the recording on this for a second. Sure. Come back, Bill. All right, looks like we're back in business now. Sorry, I just changed the batteries on the pen and it seems to be working again. All right, share. So we should be back sharing screen. Says there's sharing and let's make this full screen. All right, blah, blah, blah. Okay, pen is working again. All right, so we have two equations, two unknowns, and now the question is, how do we solve this thing? So pick your favorite way of solving systems of equations. So I'm just gonna do it this way. See, shoot, why is the pen not working again? We do not know what's up with this. Right, pause. Okay, let me see. Resume. Okay, so C1 plus C2 equals 0. C1 plus 2C2 equals -1. These are our two equations. So you write the system of equations. Right, the system of equations. All right. Now, by inspection, I can see that if I added these two together and the bottom were the opposite of the top, that the C1s would drop out. So what I'm going to do is I'm going to multiply the lower equation by -1. So C1 plus C2 equals 0. And yeah, multiplying by a constant is one of the allowed operations, plus minus 2C2 equals +1. And so this I have done times -1. And that looks like x minus 1. All right, I'm gonna write that another way. Multiply by -1. Hopefully that is more clear for you. Okay, now we add these two things together. They're always added together, by the way. So that's our system of equations. And now when you add them together, these cancel out. So now we have C2 minus 2C2, which is minus C2 equals, and we have 0 and a positive 1. So that's minus 2C2 equals 1. And then we multiply through by a -1 to get C2 equals -1. And that, my friends, is one of our answers. So we have some notes to put in here. This pen is freezing again. Why is it doing this? Hello? Okay, let's try this again. Okay, so we have some notations to make here. So multiply by -1. So that C1 drops out. And now we have, this is the answer. Adding, right, that's the result of this. And now we have, this was just to simplify. And here is the answer. Yay, okay. So now we need to go back and solve for C1. So in order to do this, we do it like this. C1 plus C2 equals 0. This was one of the equations. Select an equation from the system, preferably the easier one. I mean, why make life hard? So we do C1 plus What is C2? We substitute in the C2 value from right here, equals 0. And now we get that C1 equals 1. Ta-da! We now have the other answer. And this is just solved. And now we have our C2 and we have our C1. All right. Now, we now have our two integration constants. Yay. So what we need to do is we need to put them back into the general form. So remember that when we started this whole business, the point was to solve for C1 and C2. And here, right up here, is our general one, right? Where we had the C1 and C2 not filled in. So now what we can do is we go back and we can go ahead and fill them in. All right, so let's do it. Y of x equals C1e to the x plus C2e to the 2x. This is the general solution. To the second order linear homogeneous differential equation. Now we do y of x equals, what is C1? C1 is 1 e to the x plus C2. It's negative 1. Yeah, negative 1, right in that number. All right, negative 1 times C2e to the 2x. This is sub in. C1 equals 1 and C2 equals negative 1 from above. Those are the boundary solutions. And now we're just going to simplify this. Y of x equals e to the x minus C2e to the 2x. And we now have the solution subject to the boundary conditions. Suppose you wanted to know if that is the solution of the original differential equation. In fact, that actually should be possible to do. And what you could do is you can take this equation and you can, in fact, check to see if it is an answer, if it is a solution to our second order linear homogeneous differential equation, just the same way that we did it right here, right? This is how we checked that solution. Right there is where we did that. Okay, so we've actually done quite a lot of things today. We have taken a look at the second order linear homogeneous differential equations and understood how to recognize what that is. That's what's going on up here. And we understand that the solution to this second order linear homogeneous differential equation is solving for y, but it's actually y of x, right? It's a function. It's not just a solution like just 1x. It's actually an equation. So how do you solve this thing? Well, we follow the form that is already provided for us. And so here we are understanding how to do that. So this is the generalized form. This will be true for all the second order linear homogeneous differential equations. And then you follow the steps. Step 1 is to get the P and the Q by inspection. And we noticed that it's useful to take a look at the different kinds of notations, the Leibniz and the Newton notation. Newton can be quite useful for a lot of things. All right, so we switched over to the Newton notation, and then we lined ours up, and we were able to deduce the P and Q from this, and we substituted into the auxiliary equation, right? Okay, this is actually our generalized solution, which is why there are no numbers here. Then we figure out what the kinds of roots you have. there's three cases. And in today's example, we've had a look at two distinct real roots. And you can have a look at some of the other kinds of solutions that you could get when you're doing your homework. Case two, two real roots. Case three, complex. You just substitute into a different form, and that's it. All right, so enough theory. Here we actually went ahead and attempted to do some solutions. So here's a real equation, which we recognize we have some numbers in here. So in the generalized form, we don't have any numbers, but here we actually had some numbers. Line them up and deduce the P and Q. Here they are. P and Q have been deduced. Then what we do is we substitute into the auxiliary equation. This is basically just the quadratic equation. So here we substitute in the P and Q, and we solve this using the quadratic formula, right? Just the one that is changed up for working with this kind of equation. So we substitute it in. This gives two answers, just as it does when you use it in algebra class. You have a positive and a negative root. We got the 2 and 1, so that's what we've got up here. So once you've got these numbers, these then get substituted into your answer, right? So we take that and we select the correct form and simplify this out, right? So here it is, and we substitute these numbers in. This is the 1, and this is the 2 getting substituted in. Here is the simplified version of that. But how do you know it's actually correct? Well, just like in algebra, you can verify the answer by going ahead and plugging that back in. But it's not quite so simple because we need the derivatives. So we took a look at our differential equation here, and we said, okay, we need some derivatives. I need the first derivative and the second derivative. So here's the solution. First derivative and second derivative, we've taken those. And now we're ready to substitute back in. So we did the substitution back in. That's what all this work is here. So you simply just read off the equations and plug them in. Again, Newton notation, which is what we switched over to here, can be quite helpful. Substitute the values in, group similar terms, which is what we were doing right here. We have the C1 e to the x terms, and we have the C2 e to the 2x terms. This is the C1 e to the x terms. This is the C2 e to the 2x terms, and we put those in, and we noticed that, in fact, they do cancel out, thank goodness. And so we were questioning whether this is going to be equal to 0 or not. But we got 0 plus 0, which in fact is equal to 0, which allowed us to say that we demonstrated what we were looking for. But that still doesn't tell us about the boundary conditions, and notice that our solution at this point still has a C1 and C2 unspecified. Well, if you don't have further information, then that's the end, right? And so what you can do is you can go ahead and solve these if you have boundary conditions available. So what we did is we made some up. Well, actually, I just went and found an example, right? So you go, and what we need to do is translate those boundary conditions into things we can actually substitute things into. So we had two conditions given. Condition 1 is y of 0 equals 0, which we recognized meant that x and y are both equal to 0 in the y of x equation, right? So we pulled this equation again. That was our general solution from above, and we substituted the boundary condition in to get out our first result, C1 plus C2 equals 0. That doesn't solve it, but it gives us the first half of our result. And then we considered condition 2, which is this one right here. And this one we recognize as telling us about the first derivative. So we needed to go and get the first derivative equation, which is right here. We pulled that from above. And we got some information that y prime of 0, which is why we substituted in the 0 here, equals -1, which is why we have the answer column all being -1 over here. We got our second answer, which is another equation. So we still don't have the values for C1 and C2, but recognizing that we have two equations and two unknowns, it meant that we could go ahead and actually solve the system of equations. Sorry, just getting rid of this mess over here when the pen stopped working. And here we are solving the system of equations. I demonstrated it this algebra way, but there are other ways you could do it. And if you're more comfortable with doing it a different way, then you're certainly welcome to solve this in any way that you know how to solve systems of equations. And you get out one variable here, so I solved for C2 first, which gave me a -1. Then you pick any other equation from your system of equations and you substitute into that, and I was then able to solve for my C1. So I now have my C2 and my C1, which are the integration constants. And remember that we had the general form that did not have the C1 and C2 filled in, but now that I know what they are, I can take those and I can substitute them back in. And this, my friends, is what gave me the final solution, including the boundary conditions. All right, so I'm going to stop sharing my screen and come back and chat with you for a moment. So I hope that that was helpful in understanding how you can solve the second order linear homogeneous differential equations. You can see it takes a bit of time to do it. It's already gotten dark since we started. Some of the things we haven't done is we did not see how to use the other forms, right? So what if you got two imaginary answers, or what if you got two real roots? But those are things that you will see coming up in some of the works that we're going to be doing. So I will leave it to you to go ahead and try those out. Certainly you can ask questions about those, but it does follow very closely to what we just did here. And the good news is that solving the other equations that we're going to need to solve for the Schrödinger equation, right? Because remember what we're trying to do, H psi equals E psi. The psi is like the Y, and when you solve for the psi, it's going to tell us about where the electron is. It doesn't tell us where it is, but it will be something we can use to get the probability density, which is what gives us the electron orbitals that we know and love. So thanks so much for being with us today. I hope you find this video helpful. Sorry about all the pen issues, but it's real everyday life. All right, thanks so much, guys. And my mouse will work. I will sign off. There we go. All right, see you later. Do you really want to leave? Yes, save. Stop recording to the cloud. Yes, bye.